Okay, we can begin. So today's lesson will be the last one in this summer school. This is stochastic processes. Here is the outline of the lesson. What is a stochastic process? It consists of an experiment with a probability measure defined on a sample space and the function that assigns the time function to each outcome S in the sample space of the experiment. That's the definition of stochastic process. We can describe that on a sample space here. Here we have sample functions, and we simply do an experiment and measure a physical quantity or something like that over time. And then we repeat that experiment once more and then take another sample function. So it goes like that. When we combine all of them, it's just a stochastic process, a random process. By the way, stochastic means random. Stochastic process is equal to, or sometimes called, random process. Sample function is the time function simply associated with an experiment. An ensemble of a stochastic process is the set of all possible time functions. Okay, give me just 1 minute, please. I'm sorry. Now let's see this on examples. Here we have launching a space shuttle, and we measure the temperature on the surface of the shuttle, and we launch this shuttle many times. Okay, so we measure the temperature. For example, let's say time axis, and here is the temperature on the surface of the shuttle. This is the first launch. Okay, and we measure the temperature, let's say. Okay, here is the temperature. It increases, but that's random. So we launch once more, another time, and then we measure the temperature again. This is the launch number 2. So it goes like that. S is equal to n. Let's say we launch it n times and measure the temperature, let's say from 0, the first initial time, and goes up to, for example, how many seconds? Let's say 9,000 seconds. Okay, every second we measure it, or every maybe millisecond we measure it. So if we collect all of this n times, then this could be a stochastic process. Okay, now each of this is a sample function. And we can derive random variables from this random process by simply fixing the time. let's say, for example, here is the time. Let's say TK is 50 seconds. So what is the temperature at 50 seconds? At every 50 seconds in each launch. So we got a sample space, so we can define a random variable. Let's say let's say xk, okay, which might have values that we measured here, the temperature values. Okay, so we can define many random variables from a stochastic process. Okay. Now, in this example, you see, for example, the temperature at the time t with the launch number 175, which is 270 Kelvin. Okay. Now, if you want to get the average of this, we can try to estimate the average temperature after, let's say, this time duration, which is 217 Kelvin. And for the 117th entry launch, we can get the average temperature over the time that we measure here. Let's say this is T end. So here is T end, starting and ending. Okay. So we average from the 0 to TE and get the average temperature, which is 187.42 Kelvin. Or let's see here, example 13.3. We measure the noontime temperature in degrees Celsius in Newark Airport, in an airport, every day for a year. Okay, so here is the year, days. So let's say day 1 to day 365. Okay, so every time we measure the temperature. Here we can take, then for day 1, we get the temperature, okay, for day 1. For day 2, we get the temperature, measure it again. Day 3, we measure it. So we simply generate samples again over, let's say, midnight to 59, let's say. So we measure the temperature. Okay, this is sample function 1. And we do it 365 times. So this is another stochastic process. Now here we can measure or we can calculate average value differently. For example, we can get the average of 1 day. Okay, so this is the average of 1 day. Or we can take the average over 365 days. Okay, so there may be different average values that we can consider. Here's another example. Let's say we roll a die and record the outcome NT. We then define the random process X of t. X of t is the value of the experiment. So 1 to 6. But we do this over time. Okay, so this is time axis. This is the random process. And for this is the first experiment. I do it repeatedly. And then look at the die. If it is 1, so over a time it's 1. And then I roll again, and then it's 2, and then 6, and then 3 goes like this. Now I repeat this another time and repeat, and then create another sample function. So this is another stochastic process, random process. This could be another random process where we have 4 different symbols. Now let's see a discrete and continuous value and discrete and continuous time processes. What is discrete value process? Okay, on the right hand side you can see 4 plots. Each represents continuous time or discrete time, or continuous value or discrete value processes. Let's start with discrete value process. If the values of x of t is a countable set, then that's called discrete value process. So if we start with drawing any sample function, here is the value of the random process. If there is a set of values here, then this is discrete process. Okay? Discrete value process, sorry. Because the values are discrete here. So just like, for example, 1, 2, 3, 4, and 5. It cannot be 4.5. Okay? If it is continuous, so if there are infinite number of values here, then that's going to be continuous value process. So the process type, whether this is discrete or continuous value, it depends on the values of the random process. If it is continuous, that's called continuous value process. If it is discrete, discrete value process. Now, on the time axis, that's the same. If we have discrete values here, just like, for example, 10, 20, 30, 40, and 50. Nothing else. It cannot be 41, for example. It can be only 40. Then this is called discrete time process. If it is continuous, so at every point here, t, let's say t equals 3.014 goes like this. So that's going to be continuous time process. Then we can categorize random processes as either continuous time, continuous value. So the values here is continuously varying. Over time, it's continuously varying. There is no discrete value here. Then that's called continuous time, continuous value process. If the values over time is continuously varying, but over the value axis, it's discrete, you see, it's discrete. There are specific values that the random process could take on. So that's called a discrete value, but continuous time process. How about discrete time continuous value process? As you can see here, the values are continuous, right? There is no specific value here. It's randomly, you see, varying here. But over time, that's discrete. So at every time here, there are discrete values. Okay? Then that's discrete time, continuous value process. Discrete time and discrete value process, both in time axis and value axis, the sets are defined and all numbers are discrete. There is no continuous values over time and value. Okay, we can derive random variables from a random process. And in the previous example, for example, here, in this example, if we talk about, let's say, x 3.5, which means that actually I'm looking at t value at around, let's say, here, okay, which is 3 simply, okay, which is 3 simply. So we can derive random variables from random processes. Here, for example, we can fix the time, let's say t equals 3, and this corresponds to here, for example. So we got these values, and the set of these values simply forms the sample space. Sample space of, let's say, this is X, sample space of X, random variable X. Okay, so we can define many random variables from the random process. Okay, here is an example. We are given X of t, which has an amplitude R. So R cosine 2 pi ft. Okay, where we get magnitude, then that's X of t. Now this is random. This is random variable whose distribution is exponential, has exponential PDF, as you see. So this is a signal just like this. Here is time, and I got a sine, cosine, sorry. Varies with, you see, randomly. Okay, so here is the amplitude. So X of t. Something like this, that's rectified signal. Now, what's the PDF of the signal? Okay, first of all, X of t, since R is a non-zero, it's defined for positive values only. So R is always greater than or equal to 0, which means that X of t is 0 when t equal to t less than is 0. Okay, and for t is greater than 0, X of t is always greater than 0. Now we can write PDF. PDF simply was written probability that R, sorry, X of t, I'm sorry. X of t is less than or equal to X. Okay, so we can insert here R cosine less than X, which simply can be written as R less than or equal to X over cosine. Okay, which means that I have to integrate FR. Okay, FR. I have to integrate FR from where? From 0 to this value. Okay, so this value. When I integrate it, I got this one. So the complete CDF can be written directly. I'm sorry, this could be FX CDF. I'm sorry, this is CDF. So when we integrate it, we got this one, and then we can write the CDF here. That's exponential again. And note that here, cosine must not be 0. It should be different from 0. Otherwise, there's going to be discontinuity because that's x over 0, which is infinity, not definite. So this is valid when cosine is not equal to 0. Now we can take the derivative of this with respect to x to get the PDF. Okay, so the derivative of this function becomes this one. So here is the PDF. So IID process, we remember independent random variables. Let's say I got two random variables, x and y. Then if these are independent, then the joint PDF should be equal to the multiplication of the marginal PDF. Okay, so this was the rule. Now we extend this, but here we add identically distributed random sequences or random processes. If it is discrete, so if we talk about sequence of x, then the PMF should be multiplication of the PMF of each random sequence, okay? And the PMF here should be identical, the same, okay? Similar distribution. So if they have identical distribution, and if this condition is holds, then it's called IID random sequences. Okay, let's define then Bernoulli process. Bernoulli process, we got simply, let's take a binary generator as an example. So this generates ones and zeros, okay, randomly. Now, probability that it generates 1, probability that x is 1, let's say p, then probability that x is 0 is going to be 1 minus p, okay? Typically, p in binary signals is taken 1 over 2, okay? So this is a kind of Bernoulli process. For a Bernoulli process of x of n, find the joint PMF. The joint PMF. Let's look at the Bernoulli PMF. For any x, let's say, for x is 1, it's p. For x is 0, it's 1 minus p. So we can write p xi as, right, p xi 1 minus p 1 minus xi. Okay, how can I write this? Just remember this. For binary case, it's p times 1 minus p. Okay, so if this is, if x is 0, if x is 0, this is going to be 0, this is going to be 1. So the probability is 1 minus p. If x is equal to 1, then this is going to be 1, this is going to be 0, which is p. Okay, this is how we write this one actually. Okay, so here is the PMF of Bernoulli process. Now we can write joint PMF as multiplication of this, since this is independent from each other, and we can write this as a multiplication of these events. So simply we can write, for example, from here, let's say xi 1 minus p xi. We can write each one by one. Let's say p x1 1 minus p, sorry, 1 minus p 1 minus x1 times p x2 1 minus p 1 minus x2. So we add them up, we simply get this one, because p to the power x1, p to the power x2, so that's going to be p to the power x1 plus x2 plus xn. Since I have one here, so that's going to be p to the power, the number of sequences, which is n, and then p to the power x1, that's going to be summation again. Okay? So it goes like that. I'm sorry. So we can derive joint PMF as you see here. Poisson process. First, let's define counting process. We simply take, for example, the counting of vehicles entering in the campus of Atılım University. So, if this is the time, and if this is the number of vehicles, then when time increases, the number of vehicles entering into the campus will increase. So that's a counting process. For example, up to the time, let's say S1, we got no vehicle. After S1, there is one vehicle entering into the campus. After S2, there is another vehicle coming into the campus. So there are two vehicles coming into the campus. And then we wait until S3. So about, let's say, 3 or 5 minutes passed. And then there is another vehicle coming into the campus. So it goes like that. That's an increasing function, you see. And the time here, you see, is varying. It's about the number of vehicles entering into the campus. So N of t is a counting process. For every sample, for t less than is 0, it's 0. And that's integer valued and non-decreasing function with time. So how about Poisson process? A counting process is a Poisson process of rate lambda, where lambda is the number of cars entering into the campus per minute, for example. Okay, so lambda could be the cars per minute. In every minute, how many cars are entering into the campus? And we can then define, let's say, lambda t1 minus t0. So this is the first minute, and this could be, for example, 5th minute. So we can determine the number of cars here, and then we can determine probability of the cars, the number of cars entering within this time duration. Okay, so here is the joint PMF of Poisson process. Poisson process. You see, for every alpha 1, which is lambda times a time duration. So lambda is the number of cars entering into the campus. T1 is the time duration here. Okay, it could be here T1, this could be T2, T3. So for each of this T, we define a different alpha, and then we can find the joint PMF as the multiplication of these PMF values. Okay, how about the inter-arrival times? Inter-arrival times, simply the difference, time difference between two events. So this is the second car is entering, and at this point, the third car is entering. So this is inter-arrival time. For inter-arrival times, x1 to xn, these are IID random sequence with exponential PDF given by this formula. Okay. Here we have three theorems on Poisson processes. If we have two Poisson processes, N1 and N2, with rates lambda 1 and lambda 2, for example, lambda 1 could be the number of white cars entering into the campus in 1 minute, and lambda 2 could be black cars entering into the campus in 1 minute. Okay, this could be two different Poisson processes, and they are independent. The counting process, the number of total number of cars entering into the campus, will be again a Poisson process with the rate lambda 1 plus lambda 2. Here is an example. We have a tool booth. In the motorway, for example, we have some tools, as you may know. When we want to use the motorway, we have to pay, and there may be different vehicles there, cars, trucks, and buses, and they come to the tool booth with independent Poisson processes with lambda rates, let's say 1.2 cars per minute, 0.9 trucks per minute and 0.7 buses per minute. In a 10 minutes interval, so our T is 10 minutes. What is the PMF of N? Okay, first of all, in 10 minutes, we'll have lambda times T, let's say lambda C times T, which is 1.2 cars per minute times 10 minutes. So we got 12 cars, right? In 10 minutes. So we can calculate the total number of vehicles entering or coming to the tool booth. And it's going to be simply multiplication of the lambda, which is sum of the lambda values in here, times the time duration, which is 10 minutes. So we see that we got 28 vehicles. So for this, we simply use this formula to write the PMF of this process, which is 28 to the power n times e to the minus 28 divided by n factorial. Here, n is the number of vehicles. It might be 0, goes up to the number of, the maximum number of vehicles. Here we have two more theorems. We can simply read it. I do not want to talk about more about that. Next, let's see Brownian motion process. Brownian motion process simply describes one-dimensional random walk. Simply, for example, let's take an over a line, and I have a ball, and this ball is moving randomly, okay, over this line. So the position difference here, for example, this is position number 1, position number 2, 3, 4, 5. So here is the distance, also time, because I am moving in that way. So this motion can be modeled as Brownian motion process. It's a random process. And the positional change here is simply modeled as Gaussian. So if I take sample here, let's say Wt plus tau, and here Wt. So when I get the difference, so positional difference, T plus tau minus W of T, this is going to be a Gaussian distribution with 0 mean and alpha times tau squared standard deviation, okay? And mathematically, this can be written as here, okay, just like Gaussian process. Expected value of a process. Expected value of a process is simply expectation of x of t, which requires integration again. Here is an example. We got x of t. We got a constant, a non-negative random variable r times cosine. So this is a random process, stochastic process. And this is random variable. Then this is constant. This is noun. So the expected value of x of t is going to be expected value of r. And expected value of r is going to be integration of fr, r times fr, r dr over the range of the r. So non-negative, then it starts from 0, 0 to infinity. Okay, once we get this expected value, we can determine the expected value of the random process at time instant t, okay? So for every time instant, we got an expected value. So expected value here, expected value, actually that's a function. Autocovariance, if you are given an x of t, just like in autocorrelation, we simply covariance of x of t, xt plus tau, and autocovariance of the random sequence can also be written as this shown in here. Autocorrelation function of stochastic process is the expectation of x of t times xt plus tau. Okay, stationarity is another concept in random processes, and here we see some theorems. For stationary process, the mean value is constant, not dependent on time. Autocorrelation function is dependent only tau, and the autocovariance function is only dependent on tau. There is no t variation here. Right? For a random sequence, these are similar. So instead of t here, tau is here, we've got k. White-Sands stationary process, if the mean value is constant and the autocorrelation function is dependent on only tau, the time difference, then that's called White-Sands stationary process. White-Sands stationary process. So mu is constant and Rx dependent only time difference. Okay. We can see some properties of White-Sands stationary process, and as you can see, average power of a White-Sands stationary process is simply found by taking tau equals 0, which is the variance of the process. Cross correlation function can also be defined if we have more than one random processor. Instead of x, now we got x and y. So here we got Rx, t tau. Now here we got Rxy, t tau. Okay, the process is very similar, and we can also define jointly White-Sands stationary process. Again, we use the same idea. The cross correlation function should be dependent only the time difference, not t. Okay, we can define sequences, so jointly White-Sands stationary sequences in a similar manner. So finally, I think this was okay. This is the last example, and it's important. Now we are given a y of t, which is summation of x of t and n of t. N of t is noise, and x of t is the signal. So we can remember the problem again, cell phone problem. I got an x of t, and here we got n of t, and the output is y of t. And the mean value of x of t is constant, mu x. It's White-Sands stationary, so x is White-Sands stationary process. And x and n independent random processes. And the y of t, is this White-Sands stationary? Let's see. First, let's determine expected value of y of t. This was the rule. If it is constant, and if ry t tau is equal to ry tau, then White-Sands stationary. So let's check this. Expectation of y of t is going to be expectation of x of t plus expectation of n of t, which is mu x. Because this is mu x, this is 0, so that's mu x. How about the autocorrelation function? Autocorrelation function of y is going to be y times yt plus tau. So that's going to be x of t plus n of t times xt plus tau plus nt plus tau. So multiplication of this will give us simply x of t times xt plus tau. This is the first term, which is our x tau. Why? Because x is White-Sands stationary, so it's not dependent on time. It's dependent only on time difference. Since x and n are independent, then the cross correlation will be 0. Okay, so from here, then I can write the autocorrelation function of y as sum of the autocorrelation of x and sum of the autocorrelation of n. Okay, then our y is going to be Rx plus Rn, and this means that our y is dependent only tau. Okay, there is no t here. Then y of t is White-Sands stationary process. Our y of t and x of t are jointly White-Sands stationary. Let's check this. For this purpose, we look at the cross correlation function. So R yx. So we can write this as similar manner here. Y of t xt plus tau. So xt plus n of t times xt plus tau, which gives us autocorrelation function of x times cross correlation of nx. Since this is 0, then our yx will be rx. Then these are jointly White-Sands stationary process. How about y of t and n of t? We look at cross correlation function again, yn, ryn, which is expectation of y of t times n t plus tau. This gives us a cross correlation of xn and autocorrelation of n. Since this is 0 and this is only dependent on time, then y of t and n of t are jointly White-Sands stationary processes. Okay, finally, Gaussian processes. X of t is a Gaussian stochastic process if and only if x vector is a Gaussian random vector. Okay, and it's for k positive values only. We can similarly define Gaussian random sequence by using the same idea. We can talk about White-Sands Gaussian process when x of t is a stationary Gaussian process. We can also define white Gaussian noise where the omega w of t is a stationary Gaussian process with 0 mean and Dirac delta with Dirac delta autocorrelation function. Okay, that's the end of the semester. Oğuz, do you have any question?
Yok hocam.
Okay, so I'm gonna stop here recording.